Hello dear students, welcome in Standard 12, second chapter, part 2. Here we are taking the potential due to a point charge and potential due to the dipole and equipotential surface. Let us take potential due to a point charge. So consider a point charge Q at the origin in the figure. Take the Q to be positive. So here we calculate the work done in bringing a unit positive test charge from infinite to the point P. Here the Q's value is greater than 0. So the work done against the repulsive force on the test charge is positive since work done is independent of the path. We have taken already this theory. So we choose one convenient path along the radial direction from infinite to the point P. So at the some intermediate point P dash on the path, the electrostatic force on a unit positive charge is given by F is equal to Q into 1 upon 4 pi epsilon 0 r dash square into unit vector r dash. Here we have taken the unit positive charge, so 1 is put in the equation. Here r dash is the unit vector along the OP dash. Work done against this force from the r dash to r dash plus delta r dash is given by delta W. So work is what? It is the force into displacement, and here we take the work with the negative sign. Delta W is minus Q upon 4 pi epsilon 0 r dash square into delta r dash. It is also written as a KQ upon r dash square into delta r dash. Why the negative sign is appeared here? Because delta r dash is less than 0. So the value of the KQ upon r dash square into delta r dash become negative. But delta W is positive, so to make delta W positive, we put the negative sign in front of the equation. Now the total work done by the external force is obtained by integrating from r dash is equal to infinite to r dash is equal to r. So now we take the integration. So in the integration, W is equal to minus infinite to r dw. So it is given by minus infinite to r kq upon r dash square dr dash is equal to kq upon r dash of infinite to r is equal to kq upon r. This is our simple integration method. So we get the W total work kq upon r. By definition, this is the potential at the P point due to the charge capital Q. So W is written as V of r is equal to Q upon 4 pi epsilon 0 r is equal to KQ upon r. Now let us take another theory, potential due to electric dipole. To derive electric potential due to the electric dipole, let us take the electric dipole as shown in the figure. At the B point there is a plus Q charge, at the A point there is a minus Q charge. They are on the dipole axis. At the center point O, we are taking the two axes drawn. One is the dipole axis, other is the equator of the dipole. So at the some point P, we want to find out electric potential due to this dipole. In the dipole, we take the plus Q and minus Q charge. They are at some distance 2a. So at the P point, total potential is given by potential due to the plus Q charge and potential due to the minus Q charge. So V is given by V1 plus V2. So here take the origin as center of the dipole. Electric field as well as electric potential also obeys the superposition theorem. Thus The potential due to the dipole is the sum of the potential due to the charges plus q and minus q. So V at the P point is given by V1 plus V2 is equal to kq upon R1 plus kq upon R2, but here q is taken as negative for the negative charge, so kq upon R1 minus kq upon R2 is equal to kq in bracket 1 upon R1 minus 1 upon R2. This is the first equation. By simplifying it, draw the BM perpendicular to AP. Now AM is equal to R2 minus R1. So for the triangle BAM, cos theta is given by nearer side upon hypotenuse. That's why cos theta is written as R2 minus R1 upon 2A. This implies R2 minus R1 is given by 2A cos theta. We will put this R2 minus R1, that is 2A cos theta, in the equation 1. So equation 1 is written as Vp is equal to kq into R2 minus R1 upon R1 R2. Here R2 minus R1 is 2A cos theta. So Vp is equal to kq 2A cos theta upon R1 R2. Now q into 2A, that is the dipole moment P. So Vp is written as kp cos theta upon R1 R2. Again here magnitude of the R1 is equal to magnitude of the R2 is magnitude of the R. So R1 is equal to R2 is equal to kp cos theta upon R square. This is the general equation. Here we are taking the R greater than 2A. So by taking it, we can write V of P is equal to K P dot unit vector R upon R square. So this is the general equation. Now we are taking the another condition. So for the electric potential due to dipole, there are the two cases. Potential on the axis of the dipole. Here theta is 0 or theta is pi or 180 degree. If theta is 0, then we can take the V is equal to kp upon R square. If theta is pi or 180 degree, that is the angle between electric dipole moment and the axis. So V is equal to minus kp upon R square. So ultimately V is equal to plus minus kp upon R square. Now the potential on the equator of the dipole. For the point on the equator, the theta is pi by 2. So V is 0 always, because cos pi by 2 is 0. So ultimately V is 0. The potential at any point depend on the angle between its position vector R and the P. The dipole obtained in the limit q tends to infinite, a tends to 0 is called the point dipole. So for a point dipole, potential at any point will be exact. So for the dipole, electric field E directly proportional to 1 upon R cube, whereas for the dipole, electric potential V is proportional to 1 upon R square. So here for the point dipole, we get the exact value of the electric potential, but for general dipole we are not getting the exact value. Now potential due to the system of the charges. To find out it, first we will find potential due to every point charge and then we'll make summation. So here potential is the scalar quantity. So we get the V equal to V1 plus V2 plus V3 plus V4 plus up to Vn. So V is given by kq1 upon R1p plus kq2 upon R2p plus kq3 upon R3p plus so on kqn upon Rnp. In the diagram, at the P point, we get the position vector R from the center O, origin. Same way for the q1, q2, q3, the position vector are R1, R2, R3 respectively. For the qn, Rn is the position vector So in this 3 dimension we get the equation of the V is equal to V1 plus V2 plus V3 up to Vn. So ultimately we get the V is equal to kq1 upon r minus r1 plus kq2 upon mod of r minus r2 up to so and kqn upon r minus rn. In general, V is written as summation I is equal to 1 to n kqi upon mod of r minus ri. So if continuous distribution of charge is there, then electric potential due to it is given by, here we are taking the volume charge density. In the figure we have taken the so many charges q1, q2, q3 up to qn. So this is the system of charges. Let us take the one Gaussian surface in this sphere, that is the imaginary sphere. So here we get the uniform charge density. So for that we get the uniform charge density rho, and rho is given by summation of the charge upon volume V dash. So summation of the charge, that is the total charge, is given by the rho into V dash. So in the second equation we put the value of this charge. So V is summation I is equal to 1 to n k rho V dash upon r minus ri in mode. So this is the equation for the potential for continuous distribution of the charge. So for the continuous distribution of charge, generally we are taking the volume charge density, because here we assume there is a sphere, Gaussian sphere. Now we are taking the another point, that is the equipotential surface. What is the equipotential surface? An equipotential surface is that surface on which the electric potential at all the points are equal. For a single point charge q, the equipotential surface are the surfaces of the spheres drawn by taking this charge as the center. The potential on two such different surfaces are different, but for all the points on the same surface, the potential are equal. The radial lines of the electric fields are normal to those equipotential surface at every point. Hence, at the given points, the direction of the electric field is normal to an equipotential surface passing through that points. Suppose charge is given a small displacement. Here we are taking the unit positive charge. So dl is the displacement here. Now the work required to be done against the electric field is given by dw is equal to minus E dot dl. So dw is equal to minus E dot dl, that is the potential difference between that 2 points. But the potential difference between that 2 points on the equipotential surface is V minus V is 0. So E dot dl is also 0. But here the value of the E is not 0. The displacement is also not 0. So E dl cos theta is 0. That means cos theta is 0, because E is not 0 and dl is not 0. So cos theta is 0. That means the angle theta is 90 degree. That is the angle between E and dl is 90 degree. That means E is perpendicular to the displacement and dl is along the potential surface. Hence E is normal to the equipotential surface. At the left side, the charge, positive charge is given and its equipotential surfaces are given at different distance, and the arrow shows the electric field direction or the electric field. Same way, if we are taking the plane surface, then that the equipotential surface electric field is in the horizontal direction given, and this electric field is perpendicular to the displacement. Now let us take relation between electric field and electric potential. So consider the two closely spaced equipotential surface A and B with potential value V and V plus del V respectively. Let the P be the point on the surface B. Delta L is the perpendicular distance of the surface A from the point P. Imagine that a unit positive charge is moved along this perpendicular from surface B to the surface A against the electric field. The work done is mod of E dot dl. This work equals the potential difference VA minus VB. Thus, mod of E delta L is equal to VA minus VB is equal to V minus in bracket V plus delta V. So, mod of E delta L is equal to minus delta V. Mod of E is equal to minus del V upon delta L. Since del V is negative, so delta V is taken as the minus of delta V. So, mod of E is equal to minus mod of delta V upon delta L. So, in general it is the plus delta V upon delta L, but in general we are writing the E is equal to minus dV upon dr. So, conclusion: electric field is in the direction in which the potential decrease steepest. Second, the magnitude is given by the change in the magnitude of the potential for unit displacement normal to the equipotential surface at the point. So, here the relation between the electric field and electric potential is given by E is equal to minus dV upon dr. Dear students, now in the next session we will take the potential energy of the charge, potential energy of the dipole, potential energy due to the system of the charges in the next session.